So back in 2015, a physicist at the University of Leicester sat down and calculated the maximum mass a black hole could achieve. He really worked through the mechanics carefully. You know, the relationship between gravity and radiation pressure, and the point where a black hole's own feeding process actually starts to push matter away instead of pulling it in. He ran the numbers, and then he published his result in a peer-reviewed paper. The number he arrived at was, well, 50 billion times the mass of the Sun. The problem is, we had already found one that was larger, and honestly, we had found it decades earlier. We had measured it. We had cataloged it. We had even assigned it a name from a Mexican observatory's photographic survey, TON 618. And yeah, we had done all of that without knowing that, according to a calculation that wouldn't be published for another 40 years, what we were looking at was supposed to be impossible. For the next hour, we're going to examine every piece of verified scientific data on TON 618, the largest confirmed black hole we've ever found. What the data shows, what it contradicts, what a 2019 remeasurement means for everything we thought we knew about its size, and what it means for our models of the universe that an object this massive exists at all. This is a TON 618 full documentary, and honestly, the most important thing I can tell you before we begin is this. The scientists who study it don't have all the answers. Neither do I. That's not a caveat. That's the story. In 1957, astronomers at the Tonantzintla Observatory in Mexico were conducting a survey of the sky. It was methodical work, photographing sections of the sky, classifying what appeared. Stars, galaxies, known objects. One of the objects in the survey was unusual. It appeared stellar, a point of light with no discernible disk, just like a distant star. But its color was wrong. It was bluer than it should have been, and its brightness, for an object at its estimated distance, was off in a way that really defied easy explanation. It was logged as an unusual blue stellar object, catalog number 618 from the Tonantzintla survey. TON 618. The name is almost bureaucratic in its plainness. A dot on a photographic plate, a notation in a column. Nobody at the time knew what they were looking at. It took 13 years. In 1970, an astronomer named Marie-Helene Ulrich looked more carefully at the object's spectral signature, the pattern of light wavelengths that functions in astronomy kind of like a fingerprint. What she found were broad emission lines, light at specific wavelengths stretched and shifted in a way that indicated the gas surrounding this object was moving at extraordinary speeds. We're talking thousands of kilometers per second. That profile matched a class of objects that had only been formally recognized a few years earlier. Quasi-stellar radio sources, quasars. A quasar is not a star. It is not a galaxy. It's something more precisely described as the most violent feeding event the universe regularly produces. At the center of a distant galaxy, a black hole pulls in surrounding material. Gas, dust, the debris of stars that drifted too close. That material doesn't fall directly in. Instead, it spirals, forming a disk around the black hole. As it spirals inward, it accelerates. Particles collide. Friction generates heat. Temperatures in that disk climb to millions of degrees. At those temperatures, the material radiates, not just visible light, but X-rays, ultraviolet, energy across the entire spectrum. And when the black hole is massive enough, and the feeding is intense enough, that disk outshines the entire galaxy surrounding it. Hundreds of billions of stars, dimmed entirely by the light of a single, feeding black hole. That's what a quasar is. That's what Ulrich recognized in TON 618's spectrum in 1970. Not a star, not even a galaxy. A galaxy's entire light output, overwhelmed by the energy released as its central black hole consumed matter. If this kind of deep dive is what you come here for, the like button helps this reach more people who'd want to spend an hour on this. What makes TON 618 significant? What separates it from the hundreds of thousands of quasars catalogued since then is what came next. Once it was identified as a quasar, astronomers began to ask the natural follow-up question: how massive is the black hole powering it? That question, it turned out, would take decades to answer properly. And when the answer came, it would force the creation of an entirely new category of object, because no existing classification was large enough to hold it. The category is called an ultramassive black hole. It didn't need to exist before TON 618. To understand what that classification means and why it matters, we first need to understand what we mean when we talk about the size of a black hole. Because size here isn't length or width in any conventional sense. A black hole is defined by its event horizon, the boundary beyond which nothing can escape, not even light. Inside that boundary, the gravitational pull is absolute. Outside it, space continues. The event horizon is the edge of the black hole in the only meaningful sense, the point of no return. For a black hole with the mass of our Sun, the event horizon would be a sphere roughly 6 kilometers across, smaller than most cities. For TON 618, the ultramassive black hole at the center of that quasar, the event horizon has a diameter of approximately 2,600 astronomical units. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. It's how we measure our solar system. Earth to the Sun, 1 AU, Sun to Jupiter, 5 AU, Sun to Neptune, the outermost planet, 30 AU. TON 618's event horizon, 2,600 AU. That's 87 times the distance from the Sun to Neptune. If you place TON 618 where our Sun sits, its event horizon would not just swallow every planet. It would extend past the orbit of Neptune and keep expanding, for a distance 87 times as long as Neptune's entire orbital radius. Everything we have ever studied, every planet we have ever photographed, every probe we have ever launched, would exist inside that boundary. But even that scale comparison doesn't get at the number that defines TON 618's status as a genuine scientific anomaly. That number is its mass. And to understand how we arrived at that number, and why there is still a legitimate debate about whether it's correct, we need to look at the technique used to measure it. Because here is what most discussions of TON 618 don't mention: we have never taken a direct image of its black hole. Not the way the Event Horizon Telescope photographed M87 now. We cannot resolve TON 618 that way. It is too distant, and its quasar is too bright. The galaxy surrounding it has been completely washed out. What we measured instead was a pattern in the light, and that measurement, published in 2004, produced a number that has driven the scientific discussion of TON 618 ever since. In Chapter 2, we're going to look at exactly how that measurement was made, and why, 15 years later, a second team using the same underlying data arrived at a meaningfully different answer. Here is the central challenge in measuring the mass of a black hole at the center of a distant quasar. You cannot see the black hole. You cannot see the accretion disk around it. You cannot see the galaxy hosting it. What you can sometimes detect, if the object is active and feeding, is the light emitted by gas clouds that orbit the black hole further out, in a region called the broad line region. Gas orbiting any massive object will move at speeds determined by that object's gravitational pull. Measure how fast the gas is moving, and you can calculate the mass of whatever it's orbiting. The technique for doing this with distant quasars is called reverberation mapping. The principle is elegant. The quasar's central region pulses in brightness. That pulse of light travels outward, hits the surrounding gas, and causes the gas to glow in response. By measuring the time delay between the original brightness pulse and the gas's response, you can estimate the size of the broad line region. And by measuring the width of the spectral emission lines from that gas, which reflects how fast the gas is moving, you can calculate the mass driving that motion. The key measurement is something called the full width at half maximum of a spectral line. It's a technical term, but what it measures is physical, the spread of velocities in the gas surrounding the black hole. For TON 618, a team led by Ohad Shemer analyzed the spectral data from a set of 29 quasars. Their paper was published in 2004. They looked at the emission lines, measured the velocities. For TON 618, the spectral lines were the widest in their entire sample, indicating gas moving at roughly 10,500 kilometers per second, faster than any of the other 29 objects they examined. From that measurement, from the width of those spectral lines, they derived the mass of the central black hole. The number they arrived at was 66 billion times the mass of our Sun. 66 billion solar masses, larger than every star in the Milky Way galaxy combined. That result, 66 billion solar masses, meant that TON 618 wasn't just one of the largest black holes ever found. It was, and remains, emphasis, the largest confirmed black hole with a mass derived directly from spectroscopic emission line data. Let's put that number in terms that carry their proper weight. Our Sun contains 333,000 times the mass of Earth. It is so massive that its gravity holds 8 planets in stable orbits across billions of kilometers. It has been doing this for 4.5 billion years without interruption. TON 618 has 66 billion times that mass. That is 22 quadrillion Earths. If you assembled a line of Earth mass objects side by side, you would need 22 million billion of them to equal TON 618's mass. That line, at Earth's actual diameter, would stretch roughly 280 billion times the distance from Earth to the Sun, far beyond anything we can meaningfully picture. For comparison, Sagittarius A, the black hole at the center of our own Milky Way galaxy, the gravitational anchor of an entire spiral galaxy containing hundreds of billions of stars, has a mass of about 4 million solar masses. It is, by any ordinary standard, incomprehensibly large. TON 618 is more than 16,000 times more massive than Sagittarius A's. M87 was considered one of the most massive black holes we had measured. TON 618 is 10 times more massive than M87C's. These are not incremental differences. These are differences of orders of magnitude. TON 618 is not the largest black hole the way a taller building is taller than a skyscraper. It is in a different category entirely. And here is what most discussions of TON 618 don't show you, because there is no image to show. The mass of TON 618 was not measured by photographing it. It was not measured by looking at it directly. The quasar is so bright that the galaxy surrounding it, the entire galaxy, with all its hundreds of billions of stars, is not visible. The quasar's light has washed it out completely. What we measured was the width of a spectral line, a pattern in the light, the signature of moving gas that we cannot directly observe. The mass of 66 billion suns was inferred from a set of numbers in a spectrum. That does not make the measurement wrong. Spectroscopic mass estimation is standard, peer-reviewed methodology used across astrophysics. The result is real, but it does mean something important for the next chapter of this investigation. Because 15 years after the 2004 paper, another team went back to the same spectral data. They used a different emission line, a different signature in the spectrum. And they arrived at a different number, not a small difference, not a rounding error, a 38% difference. Both measurements are published. Both are peer-reviewed. Neither team has retracted their result. And the question of which number is correct, or whether either of them fully captures what TON 618 actually is not settled. That discrepancy is the subject of Chapter 3, and it changes the story considerably. We've now established what TON 618 is, where it sits in relation to other known black holes, and how the foundational mass measurement was made. We've established that it was described in the literature as the most massive black hole with a directly measured spectral mass. A deep dive into TON 618 requires sitting with the next section carefully, because Chapter 3 introduces a complication that doesn't resolve neatly, and it's not supposed to. In 2019, a team of researchers reanalyzed the spectral data for TON 618, not using different observations, using the same data, but using a different spectral line as their measurement basis. The result was a mass of 40.7 billion solar masses. That's 38% lower than the 2004 figure. In the context of a 66 billion solar mass black hole, 38% is not a minor calibration issue. It is the difference between a black hole that potentially sits above the theoretical maximum mass for accretion and one that sits below it. The reason that boundary matters is where Chapter 3 begins. In spectroscopy, different emission lines carry different information. They originate from different elements, at different temperatures, in different parts of the region surrounding a black hole. When two measurements using two different lines produce different results, there are a limited number of explanations. The most optimistic, one of the emission lines is more sensitive to conditions that can affect the measurement: gas temperature, ionization state, orientation of the disk. If the line used in 2019 is more susceptible to those variables, the 2004 result could still be the more accurate estimate of the true mass. The less comfortable explanation: both lines are capturing real but distinct physical conditions, and neither measurement fully represents the mass of the central object without additional information we don't yet have. The 2019 paper, authored by Jiege and colleagues, used the CIV emission line rather than the H-beta line used in the 2004 analysis. Their result: 40.7 billion solar masses, with an uncertainty margin of roughly plus or minus 4 billion. Their paper did not claim the 2004 result was wrong. It noted that the choice of emission line significantly affects the derived mass, and that the CIV line may give a more conservative estimate. Both papers are in the literature. Both results are in circulation. When you read about TON 618, you will encounter both numbers, sometimes in the same article. 66 billion in one sentence, 40.7 billion in another. Without context, this looks like a mistake. It isn't. It's an unresolved scientific question. And here is why that question matters more than it might initially appear. Two independent spectroscopic analyses, same underlying data, a 38% difference in the derived mass. And as of this recording, neither team has retracted, and no independent measurement has decisively settled the discrepancy. We do not know, with certainty, whether the mass of TON 618 is 66 billion solar masses or 40.7 billion. Those are the two published numbers. That is the current state of the science. Now consider what that uncertainty actually means. If the correct number is closer to 66 billion, then TON 618 sits above the theoretical maximum mass a black hole can achieve through standard accretion, the process of feeding on surrounding matter. We'll get to that calculation in the next chapter. But the implication is that TON 618 would represent an object that exceeds what the physics of feeding allows. If the correct number is closer to 40 billion, then TON 618 falls below that theoretical ceiling, and the model survives, just barely. The difference between those two scenarios is the difference between a confirmed anomaly and a near miss. Binary technique. Both options. Neither resolved. Either the emission line methodology has an unidentified systematic error large enough to produce a 38% discrepancy, and the true mass remains unknown, or the two lines are genuinely measuring different physical conditions, which means our current measurement techniques cannot determine the mass of the most massive black hole we've ever found. There is no comfortable middle ground between those two options. What the scientific community has done, in the absence of a resolved measurement, is to treat the 66 billion figure as the more widely cited value, because it was derived from a technique considered more directly linked to the virial mass of the central object. The 2019 result is acknowledged as a meaningful challenge to that figure, not a definitive replacement. But there is also a third data point we haven't discussed yet, and it involves a discovery made not with spectral lines, but with a completely different instrument. In 2021, astronomers using the Atacama Large Millimeter Submillimeter Array, ALMA, made an observation of the environment around TON 618 that revealed something the spectroscopic measurements couldn't capture. They found an enormous cloud of gas surrounding the quasar and its host galaxy, a structure spanning at least 330,000 light-years across. That's more than twice the diameter of the Milky Way. A cloud of gas, vast enough to contain two of our own galaxies, wrapped around a quasar we can barely see. The galaxy at the center of that cloud, the galaxy that TON 618 presumably inhabits, remains invisible. The quasar is too bright. The host galaxy has been completely outshone. This is Chekhov's gun number 3, the invisible host galaxy. The galaxy we know must be there, a galaxy large enough to contain a 40 to 66 billion solar mass black hole that we cannot see, because the black hole itself has made it invisible. We'll return to what that invisibility means in Chapter 6. For now, what matters is this. The mass discrepancy between the 2004 and 2019 measurements creates an unusual situation. One number places TON 618 above a theoretical boundary. The other places it below. And the existence of that boundary, and what it means that we're having this conversation about it, is the subject of Chapter 4. Back in 2015, Professor Andrew King at the University of Leicester published a paper in the monthly notices of the Royal Astronomical Society that proposed something no one had formally established before, that there is a maximum mass a black hole can achieve through accretion. The paper wasn't about TON 618 specifically. It was about the physics of how black holes grow, and more precisely about a mechanism that must eventually stop them from growing further. The argument involves a concept called the Eddington limit. When a black hole feeds, when matter spirals inward through the accretion disk, that infalling material releases energy as radiation. That radiation doesn't simply escape into space, it exerts pressure, outward pressure, pushing against the infalling matter. At some rate of accretion, the radiation pressure becomes strong enough to balance the gravitational pull, to slow or stop the inflow of new material. This balance point is called the Eddington luminosity. Black holes feeding at or below this rate can sustain accretion. Black holes feeding above it push their own food supply away. The Eddington limit had been understood for decades. What King's 2015 paper added was a second mechanism, one that becomes relevant only at the extreme high end of black hole masses. It involves a quantity called the innermost stable circular orbit, or ISCO, the closest distance at which matter can orbit a black hole without inevitably falling in. As a black hole's mass increases, the ISCO moves outward. And as the ISCO moves outward, it eventually reaches a radius where the self-gravity of the incoming material, its tendency to hold itself together against external forces, becomes stronger than the tidal forces trying to pull it into the accretion disk. When the ISCO reaches that radius, the accretion disk begins to break apart before it reaches the black hole. Material that was spiraling inward starts to fragment. The feeding process becomes increasingly inefficient. Eventually, for a non-spinning black hole, it stops altogether. King's calculation placed that limit at approximately 50 billion solar masses. For a spinning black hole, a Kerr black hole, the geometry is different, and the limit is substantially higher. Spin can push the maximum mass into the range of 270 billion solar masses. Most black holes are thought to spin. TON 618 almost certainly does. But here is where the conversation becomes specific to our subject. The 2004 measurement of TON 618, 66 billion solar masses. King's limit for a non-spinning black hole, 50 billion solar masses. For a spinning black hole, up to 270 billion. Three numbers. One is a boundary. One is a measured value. The third determines whether the measured value sits above or below the boundary. And we don't have that third number with confidence. What King's paper established, and what makes TON 618 scientifically significant in a way that transcends its sheer size, is this: if the 66 billion figure is correct, and if TON 618's spin is modest rather than extreme, then this object may sit near or above the maximum mass achievable through ordinary accretion. That wouldn't mean the physics is wrong. It would mean that TON 618 grew to this size through a process that standard accretion theory doesn't fully account for. Either it grew through mergers rather than feeding, black holes combining rather than eating, or it found a way to feed that bypasses the standard constraints. And you know, the universe was only 3 billion years old when TON 618 reached this size. It had, at most, 3 billion years to get there from whatever it started as. The question of how a black hole becomes this massive in that span of time is not a philosophical question. It's a technical one. And right now, the models that astrophysicists have for black hole growth don't fully answer it. Research published in the monthly notices of the Royal Astronomical Society in 2025, examining the growth histories of supermassive and ultramassive black holes across cosmic time, noted that the accretion rate per unit mass decreases significantly as black holes age, meaning the most rapid growth happens early, in the first few billion years. TON 618 appears to be a product of exactly that era. But the mechanism that seeded it, the object it grew from before it became a quasar, remains an open question. The scientific community has two primary hypotheses. We've not yet fully explored either. What Chapter 5 does is lay both of them out, with the data behind each, and ask what the honest answer is when both hypotheses are examined against what we actually know about TON 618. The answer to that question is more unsettling than most presentations of this topic acknowledge. We've now looked at two independent mass measurements of TON 618, arrived at different results, and established that a theoretical boundary exists, one that TON 618 may or may not exceed depending on which measurement is correct and how fast it spins. That's the state of the evidence. Not one clean answer, a set of real data points that don't fully cohere. Everything established in the last 35 minutes becomes the foundation for the question that Chapter 5 examines. Not what TON 618 measures, what it means that it exists at all, in a universe that was only 3 billion years old when it formed. The biggest black hole in the universe should not have been able to grow this large, this fast. The data in Chapter 5 is why this documentary exists. The universe is approximately 13.8 billion years old. The light from TON 618 that we detect with our telescopes left its source roughly 10.8 billion years ago. That means when TON 618 was producing that light, when it was at the peak of its quasar phase, the universe was approximately 3 billion years old. 3 billion years. From the Big Bang to a black hole with a mass between 40 and 66 billion times the Sun. That timeline is the problem. To understand why that timeline is a problem, you need to understand how astrophysicists think black holes form and grow. The standard model, the one that works well for most of the black holes we've studied, looks roughly like this. Massive stars form. They live out their life cycles, burning through their fuel over millions or tens of millions of years. When the most massive ones die, their cores collapse, forming black holes with masses typically ranging from a few to a few tens of solar masses. Those stellar mass black holes then grow by accreting surrounding material, gas, dust, the debris of nearby stellar environments. The growth is limited by the Eddington rate. Under ideal conditions, a black hole accreting at the Eddington limit doubles its mass in roughly 45 million years. That's the Salpeter time, the characteristic timescale for Eddington-limited growth. If you start with a black hole of 100 solar masses, a generous starting point for a stellar remnant, and let it accrete at the Eddington limit without interruption for 3 billion years, you end up with a black hole of roughly several billion solar masses, not 66 billion, not even 40 billion, several billion. To reach 66 billion in 3 billion years through Eddington-limited accretion, you would need to start with a seed black hole of several billion solar masses, not a few hundred, not a few thousand, several billion, before the accretion even begins in earnest. That's the first hypothesis, that the seeds of ultramassive black holes like TON 618 were not stellar mass remnants, but something much larger. Direct collapse black holes, objects formed not from individual dying stars, but from the catastrophic, direct gravitational collapse of enormous primordial gas clouds in the early universe. Clouds that, under the right conditions, might bypass the normal route through star formation entirely and collapse directly into a black hole with a mass potentially in the range of tens of thousands to millions of solar masses. The early universe was supposed to be too chaotic for black holes this large. There wasn't enough time. The structures weren't dense enough in the right ways. That was the standard understanding. The evidence from objects like TON 618 suggests the standard understanding was incomplete. Direct collapse black holes are theoretically viable. The conditions required, a radiation environment that prevents molecular hydrogen from cooling gas into fragmented star-forming clumps, allowing a single massive cloud to collapse whole, would have existed in specific regions of the early universe. The physics is plausible. The problem is that we have never directly observed one forming. We have proposed candidates, and the James Webb Space Telescope has been examining early universe objects that might be consistent with the direct collapse scenario. But direct collapse black holes remain a theoretical construct supported by indirect evidence. The second hypothesis doesn't require a different formation pathway. It requires a different accretion pathway, super Eddington accretion. The Eddington limit, as described earlier, is the point at which radiation pressure balances gravitational pull. But that balance assumes a certain geometry for how the infalling material is structured. If the accreting material is arranged differently, if the accretion disk is geometrically thick, or if radiation is channeled along the rotational axis of the disk rather than dispersed uniformly, then the effective limit on accretion can be exceeded. There is observational evidence that super Eddington accretion occurs. The object GNZ11, observed by the James Webb Space Telescope at a redshift of 10.6, meaning we see it when the universe was less than 500 million years old, has been inferred to be accreting at several times the Eddington rate. The physics for super Eddington feeding exists. The question is whether it can sustain the growth rates required to produce an object like TON 618. Here is where the two hypotheses, taken together, produce the most honest picture of what we currently understand. It is likely that ultramassive black holes like TON 618 grew through a combination of processes: a larger than typical seed, periods of super Eddington accretion, and possibly mergers with other massive black holes over the course of their early growth. No single mechanism, on its own, is fully sufficient, but the constraints, the available time, the theoretical growth rate limits, require that at least one of these unusual conditions applied. And here is what the honest accounting of the evidence says about how well we understand which conditions applied and in what proportion. We don't know. There is no published peer-reviewed model that fully replicates the observed mass of TON 618 at the observed cosmic epoch using only well-understood physical processes. There are models that come close. There are models that invoke less understood processes. None of them is definitively correct. TON 618 is the most massive confirmed black hole in the observable universe, and we cannot fully explain how it got that way. And as of this recording, that is not a gap in the popular understanding of the topic. It is the current state of the published scientific literature. Either our models of black hole formation in the early universe are fundamentally incomplete, missing one or more processes that operated at scales we haven't yet fully characterized, or TON 618, represents a statistical outlier that required a rare convergence of conditions we don't yet know how to predict. The distinction between those two possibilities matters. If the models are incomplete, then there may be other objects like TON 618 waiting to be found, perhaps larger. If TON 618 is a rare exception, then understanding the specific path it took could reveal something genuinely new about the physics of the early universe. Now resolve Chekhov's gun number 2. In Chapter 3, we noted that the 2019 reanalysis found a secondary signal in the CFE emission line data, a feature that the authors flagged but did not fully interpret. That secondary signal has been discussed in subsequent literature as potentially consistent with a contribution from a region of the accretion disk moving faster than expected, which would be consistent with a higher mass rather than a lower one. It doesn't resolve the 66 versus 40 billion question, but it suggests the lower 2019 estimate may not represent the full picture of TON 618's mass structure. The question of TON 618's mass and the question of how it formed are not independent. They are connected, and both remain open. After an hour with this material, it's worth doing what scientific honesty requires: a clear inventory of what is actually established and what is not. TON 618 exists. That is not in question. It is a real object, catalogued in 1957, confirmed as a quasar in 1970, and studied with multiple instruments across multiple decades. Its redshift, ZRA 2.219, places it at a look-back time of approximately 10.8 billion years. The light we detect left its source when the universe was roughly 3 billion years old. These are confirmed measurements. Its status as a quasar, an actively feeding supermassive black hole at the center of a distant galaxy, is confirmed. The emission lines in its spectrum are real. The broadline region around the central black hole is real. The fact that a massive black hole drives this object's luminosity is not in question. Its mass, specifically its classification as an ultramassive black hole, is based on spectroscopic measurements that are sound in methodology, published in peer-reviewed journals, and cited extensively in the literature. The two published values, 66 billion and 40.7 billion solar masses, reflect real uncertainty in the measurement, not disagreement about whether a very massive black hole exists. The black hole is massive by any measure. The precise figure remains under active investigation. The observation by ALMA in 2021 confirming the presence of a Lyman Alpha Nebula, a gas cloud spanning at least 330,000 light-years around TON 618, is confirmed by published data. That nebula is real. Its structure, with an inner molecular outflow and an extensive cold molecular gas reservoir in the circumgalactic medium, is a documented finding from a credible instrument. Now, the inventory of what is not established. We cannot see the galaxy that TON 618 lives in, not with current instruments at current sensitivities. The quasar's output, 140 trillion times the luminosity of our Sun, has completely overwhelmed the galaxy's starlight. We know the galaxy must be there. We cannot observe it. We have no direct measurement of its properties, its size, its stellar mass, its star formation rate, its history. The host galaxy of the most massive black hole we have ever found is, in its entirety, invisible to us. We don't know how TON 618 formed. The two primary hypotheses, direct collapse seeding and super-Eddington accretion, are both viable and neither is confirmed. More likely, the answer involves some combination of unusual formation conditions. But the specific path, the sequence of events, the reason this particular object became this massive while the universe was still forming its first structures, that path is not reconstructed. We don't know whether TON 618 is still active. The light we detect left its source 10.8 billion years ago. The quasar phase of a black hole's life ends when the available fuel is exhausted, when the surrounding gas is consumed or expelled by radiation pressure. Many quasars at similar redshifts have since gone quiet. Whether TON 618's central black hole is still feeding or has settled into dormancy, we will not know for another 10.8 billion years when the light from its present state finally reaches us. What we do know is that TON 618 represents a real edge of what the universe has produced, at least in terms of what we have found and measured. And edges are interesting not just because of what exists at them, but because of what they tell us about the space beyond them. We built the most sophisticated mass measurement techniques in the history of science. Techniques that can weigh a black hole 10.8 billion light-years away from the width of an emission line. And we arrived at two answers that differ by 38%. That's not a failure of the science. That's what the frontier of the science looks like. The uncertainty isn't hiding a cleaner truth. The uncertainty is the truth. TON 618 has a feature that I think is worth sitting with before we close. When astronomers look at the comparative sizes of ultramassive black holes, the small number of objects in this category, TON 618 stands out not just for its mass, but for the quality of evidence behind its measurement. Phoenix A, estimated at approximately 100 billion solar masses, is derived from dynamical modeling of a galaxy cluster, rather than from direct emission line spectroscopy. Its mass estimate is less tightly constrained. TON 618's mass, uncertain as it is between 40 and 66 billion, is grounded in the direct spectroscopic signature of gas orbiting the black hole. It is, in the language of the literature, one of the best documented ultramassive black holes we have. And the best documented one in the universe still has a 38% uncertainty in its mass, still has an unexplained formation history, still has an invisible host galaxy. There's a metaphor here that isn't borrowed from anywhere I've heard it before. Every generation of astronomers has drawn a map of the cosmos, defined by what their instruments could reach. TON 618 is not on the edge of our current map. It is deep in our map's interior. We have been looking at it since 1957, and it is still telling us things about the universe that our maps don't show clearly. Imagine a cartographer who has been refining the same map for 70 years, adding detail, correcting errors, filling in uncertain regions with better data, and then discovering that one of the largest objects on the map, sitting right in the middle of the territory they thought they understood, has a mass they can only estimate within a 38% margin. The map is real. The territory it represents is more complex than the map. That's where we are with TON 618. The data is real. The object is real. The anomaly is confirmed. The questions that remain are not the questions of someone who hasn't looked carefully enough. They are the questions that remain after everyone who has looked carefully enough says, honestly, that they don't yet have the answer. What the James Webb Space Telescope may eventually contribute to this picture, through its capacity to observe the environments around high redshift quasars at unprecedented resolution and sensitivity, remains to be seen. Early observations suggest JWST is finding black holes that are more massive and present earlier in cosmic history than previous models predicted. TON 618 is not an isolated anomaly. It appears to be one of the more extreme representatives of a population whose formation history we are still working to understand. We opened this documentary with a calculation. A physicist sat down in 2015, worked through the mechanics of how black holes grow, and arrived at a theoretical maximum. 50 billion solar masses for a non-spinning black hole. An hour later, the question that opened with that calculation is larger, not smaller. Because we've established that TON 618's mass falls somewhere between 40 and 66 billion depending on how it's measured, that its spin rate is unknown, that its formation history is unexplained, and that the theoretical maximum may or may not apply to an object formed in the extreme conditions of the early universe. The question is no longer just whether TON 618 exceeds the model's limit. It's whether our models of black hole formation in the early universe are complete enough to explain anything as massive as TON 618, regardless of where, precisely, the limit falls. James Webb is currently observing high redshift quasars. New mass measurements and formation history analyses are appearing in the literature on a timescale of months, not decades. The next few years of JWST data will directly bear on the questions this documentary has examined. Whether they resolve those questions or deepen them, that's the nature of this work. The universe doesn't wait for us to understand it before showing us something new. TON 618 has been showing us something new since 1957. We are still catching up. When we started this documentary, the question was simple in its framing and complex in its implications. How does a black hole become more massive than the theoretical limit we calculated for how massive a black hole can become? We now have a clearer picture of the data. The 2004 spectroscopic measurement and the 2019 remeasurement produce different answers. The theoretical maximum depends on spin, which we haven't measured directly. The formation history involves processes, direct collapse, super Eddington accretion, that are viable but not confirmed for TON 618 specifically. The host galaxy is invisible. The quasar may have gone quiet billions of years ago, or it may still be active. We don't know. What we do know is that TON 618 is real. The data behind it is real. The uncertainty in that data is real. And the fact that the most massive confirmed black hole in the observable universe still presents unresolved questions to the best instruments and the best minds working on the problem. That is the appropriate state of the science at this scale. The light we detect from TON 618 left its source 10.8 billion years ago. It has been traveling through the expanding universe, through the formation and death of generations of stars, through the evolution of galaxies from chaotic early structures to the shapes we see around us today, since before our sun existed. That light carries a specific story, the state of one object at one moment in the early universe. A black hole feeding at an extraordinary yet. Subscribing to this channel means you'll be here for the next time we sit down with something like TON 618. Somewhere 18 billion light-years from here, in a direction we can point to in the constellation Canes Venatici, the light from TON 618's present state is traveling toward us. We won't be here when it arrives, but the question it carries: how did something this large come to exist? That question is already here, and we are still working on it.